Everything you can do in linear motion, you can also do in rotation. So, one of the things we did for linear motion was we talked about the work done by a force over some distance, right? So, work was force over distance, and it's force parallel. We can do the same thing, work done by a torque over an angular displacement. That leads to so work done by a linear force, right? I mean that's redundant. Work done by a force over a distance led to a change in kinetic energy, and we use this to define kinetic energy. So work done by a torque over a displacement, an angular displacement, also leads to a change in kinetic energy. Now look, that work is not qualified as um, angular work and linear work. These are both energies, and they both have units of joules. So this kinetic energy is the same unit as linear like motion energy, but the expression we get out of it, and I'm not going to derive it here. We kind of have what we need to do that to derive it, but that expression turns out to be very analogous. It's half I omega squared. Remember, I is the moment of inertia. It's like rotational inertia, just like mass is linear inertia, and omega is angular velocity. So now what this means is if I have something that's rotating, right? If I have something that's rotating, I don't know, at some speed omega, I can now calculate its kinetic energy. If I have something that's rolling, this is interesting, right? If this is rolling, so there's an omega, but also a linear velocity, so later it's over here, still going with v and omega, it now has two kinds of energy. It's got half mv squared and half I omega squared. All right, so I need to think about the energy that it takes not just to accelerate something linearly, but also to rotate it. And that brings me to another example. All right, so we've talked about the loop. Here's an example of sending a steel ball through a loop-the-loop. All right, so an inclined track contains a 19 centimeter diameter loop, so that's the loop that we see here. Where should a steel ball be placed on the track to ensure that it goes through the loop without losing contact with the track? So you can imagine this system, right, where we say, like, okay, there's some track down in this loop. And if I start the ball too low, when it gets to here, it's going to fall. Maybe not quite like that, but I mean, it may look pretty similar to that. It'd probably go off a little more like this. Okay, so where do I need to put it? Well, a little higher than that. Thinking conservation of energy, it's got to be at least level with the top of the track, with the top of the loop, right? So if I put it right there and there is no friction, all right, so let's assume no friction for now. That will come exactly up to here. But when it gets to that point, it needs to have non-zero velocity, right? Because when it gets to that point, it's going in a circle, so it needs to have a non-zero speed so that it's so that can match the centripetal acceleration at that point. So I'm going to have to start a little higher. I'm going to have to start a little higher so that when I get to this point, so let's call this, that'll be y initial. And we'll put the ball here and call that y final. And at that point, it needs to have velocity. There's V final. V initial is 0. And that V final needs to give it that centripetal acceleration. All right? So it's a conservation of energy question. I want to remind you, so we can figure out what is V final. Well, we've done this. Remember when we did for the human loop the loop, we said the minimum speed at that point is root GR. So V final is V min at that point is root GR. We can actually calculate that for this system. Although I think what I'm going to do is just plug it in. Alright, so we have this expression. I'm also going to say we could write V final squared equals G times R. That turns out to be super useful. Again, you could calculate a number at this point, but that's not the way I like to do this. So, so we're just going to use conservation of energy. So E initial equals E final. E initial is all gravitational potential, right? In fact, I could say K plus U equals K plus U. This is initial, final, and final. So K initial is 0. K final is a non-zero thing. U final is non-zero, right? We're often going from the highest point to the lowest point, but here we're going from the highest point to another less high point. So those are both non-zero. So let's plug in an expression for this. I've got mg y initial equals half m v final squared plus mg y final. So that's almost all of it, but that's not all of it, right? Because I need to include the fact that this thing is rotating as well. So if this was all I did, I would underestimate how high this needs to be, right? Because the gravitational potential needs to go not just into linear motion, but also into rotational kinetic energy. All right, so I'm suggesting I need to add one more term in here. Let's move that a little further. Which is half I omega final squared. Okay. So that's really the difference between conservation of energy in the last chapter and conservation of energy now, is I'm thinking about not just linear motion but also rotation. Otherwise, this should all look kind of familiar. Okay, so we can think about what are some of these numbers. Well, y initial is what we're looking for, right? We're solving for, let's circle it this way. That's what we're solving for. I know the mass of the ball, I think. Oh, I don't know the mass of the ball, but you know what? It's going to be okay. I'll tell you why. It shows up here, here, and here. And I is, let's assume it's a solid sphere. Right? It's a ball bearing, so it's spherical. The moment of inertia for a solid sphere is 2/5 mr squared. So we'll just plug that in there. We just have to be careful about what those are. So that's 2/5. M is the mass of the ball bearing, and R is the radius of the ball bearing. So I'm going to call that capital R squared. Okay, this is good. So here's the next, well, how is this going to work out? Because I don't know the radius of the ball bearing. Yeah, yeah, but look, check this out. Omega, pardon me. Omega final is V over R, right? So remember, V equals omega R. So omega final equals V final over R, and I'm squaring it. So if I put those terms together, that means this term, this half I omega final squared, it's not half. No, it is half. It's half times 2/5 to, no, 25, m r squared times omega final over r, no, sorry, not omega final, v final over r squared. You see the r's go away? So what I get out of that whole thing is a half times 2/5 times v final squared. Awesome, awesome, that's great. So all I get out of this is a factor, the half, because it's kinetic energy, and the 2/5 because it's a sphere. So all that matters is the shape of the object. All right? Okay. So let's plug in another line here. So I've got m times g times y initial. Those are all numbers we know. Well, we don't know the mass, but we're going to divide it out in a second. Y initial, which we know, we're solving for, equals half m v final squared. V final I have an expression for, so we'll plug that in a second, plus half, we just said half I omega squared turns out to be half 2/5 v final squared, so half 2/5. There's a mass term that I missed. Mass times v final squared plus mg y final, which I know. Okay, now we can divide out the mass. Ah, this is fun. Okay, so mass, 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 and mass all go away. So we're really, really close here. So what else do I know? V final squared. V final squared is GR, right? V final squared is GR, so I can plug that in. Oh, we're so close. So G times Y initial equals half times GR. R here, yeah, let's leave it as R. That's the radius of the loop. I think we know the diameter of the loop. So here. So that the diameter of the loop is 19 centimeters. That's Y final, right? Y final is 19 centimeters. And the radius of the loop is 19 centimeters divided by 2, right? Which is 9.5 centimeters. Okay. Oh, we're so close. So G times Y initial equals half GR. Again, V squared is GR, so that's good. Half 2/5 V squared again, so that's another GR, plus G times Y final. Now look, I can divide out G. Let's use a negative, or red. Look at that. So the planet doesn't even matter. The planet doesn't matter. The time this will take depends on G, but the actual starting height, G doesn't matter. Now, that's if we don't include friction, so I expect this to change if we did. Okay, one more line. So Y initial equals half times R plus half times 2/5 times R plus Y final. Okay, so plugging into that, again, we know all those numbers. I'm going to move one line below the next instructions. Okay, so half times R, we can plug that in. Half times, let's leave it all in centimeters at this point. So R is 9.5 centimeters plus half times 2/5 times 9.5 centimeters plus 19 centimeters. And if you do that, you get 26 centimeters. Great. So that tells me where I need to go, right? This equals 26 centimeters. And I actually have this demo, this exact demo. Not with me, but I have done this before. And I've placed the ball at 26 centimeters. And you know what happens? It doesn't go through the loop. It doesn't go through the loop. Does that mean our math was wrong? No. It means that one of the assumptions that went into this problem was wrong. The assumption that there is no energy loss is absolutely wrong. Because when you roll this ball down the incline, you can hear it. All right, it's like metal on metal, the ball rolling. You can hear it, but sound takes energy, and that energy has to come from somewhere. Specifically, it's coming from the initial gravitational potential that the steel ball bearing had. So you have to actually put this up a little higher. So what I've done is I've put this up a little higher and a little higher until it just goes through the loop. So in reality, so this is like Y initial theoretical. Y initial experimental is 34.5 centimeters. So we could ask, like, okay, how much energy then are we losing to friction? Well, the answer is that the increase in potential energy, right? It should really just be mg times the extra height we had to add to this thing. It turns out if you do that, it's something like 25 millijoules. So yeah, any problem where we have rolling motion, we should think about the rotational kinetic energy as well as the linear kinetic energy.